Okay, now let's talk about section 7.5, unit circle approach, properties of the trigonometric functions. Okay, so the first we are going to use the unit circle to find the trig values for arbitrary number. Okay, so first unit circle, we have this xy coordinate system, and we have a circle centered at origin with a radius 1. So here's number 1, here's number 1, here's -1, here's -1, this is 0. And there is a vertical line through the point 1 on the x-axis. We are going to do the following thing. For a positive t, for example, here you get a segment with length t. Okay, and then you're going to wrap this string around the circle, unit circle. It has an image here. This is a point, let's call it P. This point P, we have x and y coordinate A and B. Okay, so first you have this point, let's call it Q. You wrap this string along the unit circle, you get the image P. P has xy coordinate A and B. So because you wrap it around the unit circle, so from this point 1, let's call it A, the arc AP has the length T. T is the length of QA. So here we assume this is the top. If T is negative, we're going to choose here. If T is negative, this is Q prime, and then you're going to wrap the bottom string around the circle in the clockwise order. So the negative, positive, you have the similar stuff, and the length is Ups value of T is negative T. Okay, and when we have this, we have the following definition. After we get this setting, we have the following definition. The definition is the following. So let T be a real number. And let P, which is AB, be the point on the unit circle that corresponds to P in this sense. Then we define six trigonometric functions. They are sine of t. Sine of t is just b. Cosine of t is a. Tangent of t is b over a. Okay, then remember that there are relations among all six trig values. These three are the first level, and the other three are the corresponding reciprocals. So cotangent t is a over b. Secant of t is 1 over a. cosecant of t is 1 over b. When it is well defined, when they are well defined. Here when we say they are well defined means that the denominator is not 0. Either a is not equal to 0 or b is not equal to 0 respectively. Okay, so this is the 6 trigonometric functions for arbitrary numbers. At this moment, we don't interpret these number t as angles. We just get a general number and define the trig values. Okay. So for example, find the values of sine t, cosine t, cosecant tangent t, cosecant t, secant t, and cotangent t. Cosecant t, secant t, cotangent of t, if p is negative 1/2, negative square root of 3 over 2. Okay. If this point is the point on the unit circle, that corresponds to the real number t. So you see here, in this computation, we actually don't care what t is, we care its image. If for different t they have the same image, then you have the same trigonometric values. We don't know if this will happen or will not, but we just have this corollary so far. If for different t, possibly if for two different t, they share the same corresponding point p, then they will have all the same 6 trigonometric functions. You will see it later, but now we just get this from the abstract discussion, because the trig values are defined by the xy coordinates of a p. So solution. Remember, sine of t is y coordinate, so you just get a y coordinate of p. Cosine of t is x coordinate. Tangent of t, b over a is actually y over x. You will see it is a square root of 3. Okay, just multiply top and bottom by -2, you get the square root of 3. Okay, once you finish the first line, you just flip them to get the second line. So the cosecant of t is -2 over square root of 3. Secant of t is -2. Cotangent of t is 1 over square root of 3. Okay, so that's not bad. Okay. So far we have the 6 trigonometric functions for arbitrary real number. The real number may not be the angle, it's just a general number. Now we want to apply this process to the angles. So the trig angles, trigonometric functions. Trigonometric functions of angles. So what is the meaning of it? So first, let's place this angle in the standard position. For example, let's just put this here. theta. Okay? And then, because we're trying to use a unit circle, let's draw the unit circle. Unit circle is here. This is unit circle. Unit circle has a radius 1. So this is 1 and 1. Here is also 1. Here's negative 1. Here's 1. Here the 1 means that the radius is 1. Okay? Then, once you have this angle theta in terms of reading, theta is in reading. Theta is in reading, then the corresponding arc has length, let's call it t. The corresponding arc has length t equal to theta times radius. Radius is 1, so t is equal to theta. In our setting, radius is 1. It's very important. Okay? And you see, theta is t when you use a reading to measure it. Okay, then we have our definition. We define for the angle theta in reading, the sine theta is defined to be sine of t. Here, this t is just a general real number. Here, this theta is interpreted as an angle. So this is a number. This is a measure of an angle. They are connected by this formula. Arc length is equal to the reading times the radius. Okay, so the definition of an angle is defined to be the definition of the corresponding arc when the radius is 1. Very important. This part, radius must be 1. If the radius is not 1, then your answer is not correct. Okay, so the cosine of theta is cosine of t. Tangent of theta is tangent of t. A similar thing, cosecant of theta is cosecant t. Secant of theta is secant of t. Cotangent of theta is cotangent of t. Okay, so that's the trigonometric functions for general angles when you have the corresponding arc, corresponding reading angle. Okay. Okay, so that's the stuff we have, and we know that. So first, let's say here we fix the radius to be 1. So we always put this as our hypothesis. We fix the radius to be 1, and in order to get t, the theta is in reading. But to get t, that's not important. We actually need the corresponding point P. Okay, so this is the important thing we need. We need the point P. T is used to determine P. But to get this P, you see, P is here. This is the point P. This is the point P. To get the point P, it doesn't matter. We use reading or degree. Okay, so to find the t, we do need the reading, but to find the point P, we don't need the reading. We don't have to use reading. We can use degree. Degree, you get the terminal side. The terminal side intersect with a unit circle. You will get P. Okay. Okay. So when you define the trig value, for example, when you define the sine of pi over 2, or when you try to compute the sine pi over 2, you can write the sine pi over 2, or you can write the sine 90 degrees. There's no difference about these two units. So you can either use reading or use the sine degrees. Okay. Okay. So that's a stuff. So the reading. So what I'm trying to explain is that the reading is used to get t, and t is used to get p. P is used to get the trig functions. But the degree can also give you P. Remember, degree can also give you P. P give you the trig values. So they are just two different approach to the same point. Okay. Okay, so in this part, we need to focus this piece on the unit circle. It's on the unit circle, very, very important. If you use a circle centered at the origin with radius r, if you have this condition, it's not radius 1, then from similar sectors we have that, you see here, we have this is intersection with P, this is intersection with P prime. We have that this party will have A, B, this party will have A prime, B prime. You will have the B prime over R is B over 1, and any other relation. So A prime over R is A over 1, and there will be, okay, this is equal to sine of theta. This is equal to cosine of theta. Okay, and once you have sine and cosine, you can define other four trig values. Okay, so if you have a different radius, you have to divide A and B by the corresponding radius. Okay, so that's the thing I want to mention. The similar sector just means this large sector, or let's say this large sector is proportional to the small sector. So that's similar sectors. But anyway, if you can use radius 1, just focus on the radius 1. Okay. Okay, now let's see the example. Okay, so find the exact values of each of the 6 trigonometric functions of an angle theta if 4, -3 is a point on its terminal side. Okay, so assume we know one point on its terminal side. We're looking for all 6 trigonometric values. First of all, let's sketch it for -3. So for x coordinate is 4, so it's 1, 2, 3, 4. Y coordinate -3, 1, 2, 3. This is -3. This is 4. Here. So 4, -3. And the corresponding radius, this is radius. Radius is the distance between the point and the origin. Okay? So the radius is what? Is the square root of 4 squared plus -3 squared. It's 16 plus 9 is square root 25 is 5. Okay, so this is a radius. You get this formula by the Pythagorean theorem. Okay, so once you get the radius, then the sine of the angle theta is b over r. B is -3. R is always 5. And cosine of theta is x over r. And then you get the sine of a cosine, you get the tangent of a theta is -3 over 4. Tangent is a sine over cosine is a b over a. And cosecant theta, you flip it, it's -5 over 3. Secant of theta is 5 over 4. Cotangent of theta is -4 over 3. So that's all 6 trigonometric values. Okay, so here we don't care the values of angle. We just determine one point on its terminal side, and then that is enough. Okay. Okay, so that's the definition for the trigonometric functions of any angles based on the unit circle. So this is not unit circle, but it's proportional to the unit circle. So you're going to divide by the radius r. That is like the constant. Okay, then next we're going to study the domain and the range of those 6 trigonometric functions. Well, first of all, sine. Remember, sine is equal to b. Sine is equal to b. That's just this point. And this is unit circle. Again, it's a unit circle. Sine is equal to b. B, every point has a b coordinate, has a y coordinate. So its domain is a set of all real numbers. Okay, so the domain of a sine function is a set of all real numbers. And the cosine is equal to a, the x-coordinate. Sure, x-coordinate exists for all the points on the unit circle, so the domain of cosine is a set of all real numbers. Okay, so that's a natural stuff. And next, tangent. Tangent theta is b over a. The tangent of theta is b over a. Here, whenever you have a ratio, you have to guarantee the denominator is not equal to 0. Okay, a is not equal to 0. A is x-coordinate. Only for the point on the y-coordinate has x-coordinate 0. So only this point and this point, these 2 points have x-coordinate equal to 0. Okay, this point, the top point corresponds to the angle pi over 2. The bottom point corresponds to the angle 3 pi over 2. So the domain of tangent function is a set of all real numbers except odd integer multiple of pi over 2. So here's pi over 2, here 3 pi over 2. So you skip the 2 pi over 2. Pi over 2 is this point. So that this point is a good point for the tangent. So pi over 2, 3 pi over 2, then you go back, you will get a 5 over 2, 7 pi over 2, 9 pi over 2, 11 pi over 2. So it's a odd integers of pi over 2. Okay? So this is a domain of a tangent function. It is the set of all real numbers except the odd integer multiples of pi over 2. And the similar thing happens for what? For the case when a is the denominator. You see that the secant theta is 1 over a. Check that. Secant theta is 1 over a, so a cannot be 0. So the domain of secant function is the set of all real numbers except odd integer multiples of pi over 2 also, because they share the same denominator. They share the same denominator, they will avoid the same angle. Okay? So this is a sine cosine. Sine cosine, no restriction, all real numbers. Tangent cotangent, odd multiples of pi over 2 are not allowed. And the similar thing, we get tangent, a cotangent and a cosecant. Cotangent of theta is a over b, and the cosecant of theta is 1 over b. So b is not equal to 0. Check here, 1 is b equal to 0. These 2 points, left and right point. Left point, the angle is 0, t is equal to 0. Sorry, right point, t is equal to 0. Left point, t is equal to pi. 0, pi, 3 pi, 4 pi, 5 pi, 6 pi. So they are the multiples of pi. So the domain of cotangent, cosecant functions are the set of all real numbers except integer multiples of pi. Okay, so just right left point b is 0, top bottom point a is 0. So let's put it here. Okay, so we just label them here. Top bottom a is 0, left right b is 0. So they are both excluded for the corresponding trig functions. Okay, so that's our domain of 6 trig values. And then we talk about the range. The range, you see here, the sine is b, cosine is a. b, so you see here, the whole circle, a whole unit circle is in the in the horizontal band, -1, +1. So B is at the most +1, at least -1. So B is between -1 and +1. This is for B, the y part. And A is a horizontal distance, so this is for A. A is at the most 1, at least -1. Okay, so this is the range of sine and cosine. So if you want to write it, you will say that the sine of theta is between -1 and +1, and the cosine of theta is between -1 and +1. Okay, so that's the stuff. For the reciprocal, whenever you flip a small number, you actually make it bigger. So when you flip 1/2, you get a number 2. When you flip -1/2, you get a -2, negatively large. So what we have, when we flip the sine, you get a cosecant. So the cosecant theta, it could be less than or equal to -1, or cosecant theta is greater than or equal to +1. And similar thing happens for the reciprocal of a cosine. Secant of theta could be less than or equal to -1, or secant of theta could be greater than or equal to +1. Okay, so what is the detailed correspondence? So when sine theta is between -1 and 0, sorry, 0, it's -1 and 0, the cosecant theta is less than or equal to -1. When sine theta is greater than 0 and less than or equal to 1, cosecant theta is greater than or equal to 1. When sine theta is equal to 0, cosecant theta is undefined. Cosecant theta is undefined. In this case, theta is k pi, any integer multiples of pi. So this is for sine. For cosine, when cosine is between -1 and 0, secant of theta is less than or equal to -1. When cosine is between 0 and 1, secant of theta is greater than or equal to 1. When cosine theta is equal to 0, then secant theta is undefined. In this case, theta is k pi plus pi over 2. K pi plus pi over 2. It's always some multiples of k pi with additional pi over 2. Okay? And secant and cosecant are never 0. So cosecant theta, secant of theta cannot be 0 because they are reciprocal, 1 over something. So numerator 1 is not 0, so the secant and cosecant are not 0. And for the tangent and the cotangent, these two functions, they are defined either by b over a or a over b. So they are from -infinity to +infinity, which means it can take whatever, any value. So tangent theta can be 0, tangent theta can be positive, can be small, positively large, negatively small, negatively large, 0, everything. So on the table 6, on the page 556, table 6, on page 556, table 6, you will have the collection of the domain and the range. Okay, so if you want, you can also go through this and check what is the domain and the range. So there's no, this part there's no tedious discussion, it's just observations, okay? Okay, so for the trigonometric functions, remember we only care P. The position P determines the sine, cosine, tangent, and cotangent. We mentioned for different T, they may correspond to the same point P, okay? So the correspondence is the following. Whenever you have a complete round or revolution, you go back to the original point. For example, you have a point P here. You can go just for one shortest round, you get a theta. Or you can go one revolution and go to the P, same point P. Okay, so you can go one revolution, two revolutions, three revolutions, or you go opposite directions. So whatever direction, one round corresponds to 2 pi. Clockwise give you negative 2 pi. Counterclockwise give you positive 2 pi. So from this observation, we can see that sine of theta plus 2 pi times arbitrary constant k. You get additional revolutions. Since this revolution, one complete revolution does not change the terminal side, so it is equal to sine theta. Once you have the same terminal side, you have the same trigonometric functions. And similarly, cosine of theta plus 2 pi times k is cosine of theta. Okay, here k can be any integer. K can be any integer. Okay, this is summarized as a definition, as a property for the function. The definition of the function. Okay, so a function f is called periodic. Periodic if there is a positive number P such that whenever theta is in the domain of f, so is theta plus P, and f of theta plus P is f of theta. Okay? The smallest positive P with this property is called the fundamental period. Of f. Fundamental period of f. Okay? So from the computation, we can see that for sine and cosine, one complete revolution will give us the period, and that's the smallest positive number with the property. So the periodic property is the following. For the sine, you need 2 pi. Cosine, you need 2 pi. Because the cosecant and secant, they are just just a simple reciprocal of sine and cosine. So the cosecant need 2 pi as a fundamental period. Secant needed 2 pi. And tangent cotangent, because they are the ratio of sine and cosine. Sine and cosine may change the sign together. So tangent and cotangent have the fundamental period pi. Okay, so this is a periodic properties. This is on page 557. Okay, so when you know the periodic property for the trigonometric values functions, so you can easily determine the value for some large or weird numbers, weird angles. So for example, if we want to find the sine of 420 degrees, so it's too big, so we just subtract 360 degrees, because it's exactly 2 pi, so you minus 360 degrees. 360 degrees, what is it? It's 60. Sine 60 degrees, root 3 over 2. Sine 60 degrees, root 3 over 2. Okay? And another one, tangent 5 pi over 4. 5 pi over 4 is a large angle, so tangent has fundamental period pi, so we subtract the pi. 5 pi over 4 minus pi is pi over 4. Tangent pi over 4, tangent 45 degree is 1. Okay? And the cosecant 11 pi over 4. Cosine 11 pi over 4. Okay, so what's that? Cosine 11 pi over 4. So cosine has period 2 pi. So 11 pi over 4 minus 2 pi. 2 pi is 8 pi over 4. So it's 3 pi over 4. 3 pi over 4, if you check the table, it is going to be negative square root of 2 over 2. Okay? Negative square root of 2 over 2. So this is a way to transform the large angle into the proper domain, so that you can memorize or recall the formulas, recall the angles, the angle values. Okay. Okay. So next we're going to study the even odd property. Okay. So symmetry. Remember, we say f is even or even function if f negative x is fx. F is odd if f negative x is negative fx. Okay, so this is an even and odd property. That's the definition. And the theorem for the trigonometric functions is the following. So there are 6 trigonometric functions. We know that sine is an odd function. Cosine is an even function. And from here you can get tangent is an even function. Tangent is an odd function. Cotangent is an odd function. And cosecant is an even function. Cosecant is an odd function. Secant is an even function. Okay, so that's periodic, the even odd properties. So you just memorize. in those 6 trigonometric functions, only cosine and secant, they are even. All other 4 trig functions are odd. Okay, so why? Let's just use x and y to demonstrate. Okay, so here is a theta. Here is a negative theta. For this point of a P, you have A and B. For this point of a P prime, because they are symmetric, so here is a, the same A, but B becomes negative B. So for this reason, the sine of negative theta is equal to negative B, and the sine of theta is equal to B. So combine this, we get the sine of negative theta is negative sine of theta. Negative sine of theta. And same thing, you see here, from here you get the cosine of theta is A. Cosine of negative theta is also A. For it doesn't matter, you just use the x coordinate. So this implies cosine of negative theta is cosine of theta. And other 4 trig functions, you just use sine over cosine, 1 over sine, 1 over cosine, you can get the same thing. So only cosine, secant are even. Other 4 trig functions are odd. Okay? Now let's see the example. Okay. So first, sine negative 45. Sine negative 45, sine is an odd function, so you get a negative sine 45. Sine 45 is square root of 2 over 2, so you get a negative square root of 2 over 2. Okay? And second, cosine negative pi. Cosine even function, only cosine secant even. Cosine even function, you ignore this the negative sign. And the cosine pi is negative 1 from the memory. Cosine pi is negative 1. It's x. X is the left point. And cotangent negative 3 pi over 2. It is negative cotangent 3 pi over 2. Okay? Cotangent 3 pi over 2 is equal to 0. So it's negative 0 is 0. Cotangent 3 pi over 2 is equal to 0. It is A over B. Just check the definition. You see, it is A over B. And tangent negative 37 pi over 4. 37 pi over 4. Wow, it's a huge number. So whatever, you just get, you first move the negative sign forward, you get 37 pi over 4 with negative sign. It's an odd function. And 37 is a 32 plus 5 pi, so it's a negative tangent. We don't need 32, we need 30 what? 36. 36 is a 9 pi plus pi over 4. Okay, not 32. 36. 9 pi plus pi over 4. And the tangent has a period pi, so this 9 pi disappears, so it's a negative tangent pi over 4. Pi over 4, tangent pi over 4 is 1, so it's negative 1. Okay, so again, whenever you have no idea about this, try to memorize for the unit circle sine theta b, cosine theta a, tangent theta b over a, cotangent theta a over b. Okay, so this is a 3 pi over 2. If you don't get it, this is a 3 pi over 2. So at this point, it has x coordinate 0, y coordinate negative 1. So that gives you cotangent of 3 pi over 2 equal to 0 over negative 1 equal to 0. And tangent pi over 4 is here. This is a square root of 2 over 2, square root of 2 over 2. So tangent pi over 4 is equal to 1. Pi, cosine pi is here. It has a x coordinate negative 1, y coordinate 0. So that's why the cosine pi is negative 1. Okay, so if you still don't memorize the table, just use this unit circle to get the answer. Okay, so that's the section 7.5, the unit circle approach. So you always get a unit circle and do the corresponding evaluation. So just do your assigned exercise. Make sure you can find all the values. Again, try to get the following table when you have 0 reading, pi over 6 reading, pi over 4 reading, pi over 3 reading, pi over 2 reading. Let's see the sine theta. Sine theta will be 0, 1/2, root 2 over 2, root 3 over 2. Sine pi over 2 is 1. So we're going to memorize it like root 4 over 2. And then you go slightly bigger. It is going to be like, it's 2 pi over 3. This is 2 pi over 3, 2 pi over 3, then 3 pi over 4, 5 pi over 6, and pi. Then you just, this here is increasing, and then you get a decreasing. Root 3 over 2, root 2 over 2, 1 over 2, and 0. And cosine is similar. So you get 1 is a root 4 over 2, root 4 over 2. Then you get a root 3 over 2, root 2 over 2, 1 over 2, and 0. And then you go to negative 1/2, negative root 2 over 2, and negative root 3 over 2, and negative 1, negative root 4 over 2. This is a 1, negative 1. Cosine pi is equal to negative 1. So try to use this kind of pattern to memorize it and use this to do your exercise. Okay? Okay, we'll stop here. Thank you.